The Faraday paradox is a fascinating and mind-bending concept within the field of electromagnetism. At its core, it presents an apparent violation of Faraday's law of electromagnetic induction, one of the fundamental principles of electromagnetism. To understand this paradox, it's essential first to grasp Faraday's law and how it normally operates in classical electromagnetism. Faraday's law, formulated by Michael Faraday in 1831, is one of the cornerstones of electromagnetism. It describes how a time-varying magnetic field induces an electric field. In simple terms, it tells us that a changing magnetic field can produce an electric current in a conductor. The key idea here is that the electric field generated by a changing magnetic field is not conservative, meaning it doesn't come from a potential field in the usual way that static electric fields do. Now, let's introduce the Faraday paradox, which originates from an experiment that seems to defy this law. The paradox can be illustrated through a thought experiment often called the Faraday disk experiment. Imagine a large conducting disk rotating in a magnetic field. The setup goes like this. You have a circular conducting disk like a metal plate. The disk is placed perpendicular to a uniform magnetic field, and the disk starts rotating at a constant speed. If we apply Faraday's law, we expect to see a change in magnetic flux as the disk rotates, which should induce an EMF in the disk. The problem, however, arises when we try to figure out how the induced current behaves. As the disk rotates, the magnetic flux through different parts of the disk changes. According to Faraday's law, this should induce an EMF. The paradox is that, as per classical theory, the induced EMF should be distributed uniformly along the radius of the disk. However, in practice, this is not what happens. Instead, the current behaves in an unexpected way. In a conducting loop like this, we would expect the electric field to be radially symmetric due to the rotating magnetic field. Faraday's law suggests that the induced current should depend on the angular velocity of the disk and the strength of the magnetic field, and it should induce a circulating current that flows in the disk. But here's the twist. The current that actually forms appears to violate Faraday's law because the expected EMF does not manifest in the way classical electromagnetism predicts. To understand why this happens, we need to examine some assumptions built into classical electromagnetism. Faraday's law assumes that the magnetic field is uniform and the geometry of the conductor remains unchanged. In the Faraday paradox, though, the disk is rotating and the magnetic field interacts with it in a way that violates some of the assumptions of the law. The rotating disk essentially sets up an unusual situation in which the velocity of each part of the disk changes as a function of its distance from the center. The rotation creates different speeds at different radial positions, and this affects the motion of the charges in the disk. One might expect that this velocity gradient would lead to an induced EMF that increases radially. However, this is not the case. Instead of a uniform induced current, the paradox shows a non-trivial and seemingly contradictory behavior in the distribution of the induced EMF and the resulting current. To resolve this paradox, it is necessary to consider the concept of electromagnetic potentials, specifically the vector potential and the scalar potential. These potentials are essential tools in electromagnetism because they allow us to describe the electric and magnetic fields in a more generalized way. In the case of the Faraday paradox, the magnetic field is not only changing in time, but the conductor, the rotating disk, is also in motion. This motion means that the disk is experiencing not only a changing magnetic field, but also a changing vector potential. The vector potential itself contributes to the electric field and therefore to the induced EMF. This is crucial because in a rotating disk, the apparent violation of Faraday's law can be explained when we account for the contribution of the moving system to the electromagnetic potentials. The rotating motion introduces complexities that aren't captured in the simpler versions of Faraday's law. In this scenario, what happens is that the magnetic field is inducing an EMF, but the distribution of the induced electric field is not uniform because of the peculiar geometry and motion of the disk. The induced current behaves in ways that suggest a deeper interaction between the magnetic field and the electric potential than Faraday's law in its standard form accounts for. Another piece of the puzzle is Lenz's law, which dictates that the direction of the induced EMF opposes the change in the magnetic flux. In the rotating disk case, this law is still valid, but the paradox arises from the fact that the induced current doesn't behave as expected. The problem isn't that the current doesn't oppose the change in flux, but rather that the distribution of the induced current seems inconsistent with the classical understanding of Faraday's law. It's crucial to emphasize that Faraday's law itself is not actually violated in this situation, but the paradox stems from our inability to apply the law directly in this rotating system using conventional methods. What seems like a violation is actually a result of not fully accounting for the complexities introduced by the motion of the conductor in a time-varying magnetic field. The key takeaway from the Faraday paradox is that the law of electromagnetic induction is deeply tied to the reference frame from which you observe the system. When you consider the disk's motion and the transformation of electromagnetic potentials, the paradox can be resolved. It's a beautiful example of how classical electromagnetism interacts with relativity and the complexities that arise when motion is involved in the system being studied. To further grasp the Faraday paradox, we must expand our understanding of electrodynamics. Modern approaches, such as relativistic electromagnetism, incorporate the effects of motion more accurately than the simpler classical model. In relativistic electromagnetism, we learn that the electric and magnetic fields are not independent, but are instead intertwined in a way that depends on the observer's frame of reference. This realization helps explain the paradox, as the rotating disk setup can be seen as an example of how different observers might perceive the electric and magnetic fields differently. A moving observer might not see the same magnetic field or the same electric field as an observer at rest, leading to a different interpretation of the induced EMF. Moreover, in relativistic terms, the motion of the conductor changes the observed configuration of the electric and magnetic fields, leading to the unusual behavior observed in the Faraday paradox. This deeper understanding provides a more consistent explanation and eliminates the seeming violation of Faraday's law. The Faraday paradox is not a true violation of Faraday's law, but rather a fascinating and complex consequence of the way in which electromagnetism works when we take into account motion and the transformation of electromagnetic potentials. It reveals the limitations of applying Faraday's law in certain contexts without considering the full complexity of the system. In essence, the paradox encourages us to think beyond the classical laws of electromagnetism and to embrace the more nuanced relativistic views that modern physics provides. The rotating disk experiment and its paradoxical outcome highlight the intricate relationship between electric and magnetic fields, the nature of induced currents, and the subtle influence of motion on electromagnetic potentials. Far from undermining the validity of Faraday's law, the paradox offers a deeper insight into the nature of electromagnetism, showcasing the importance of considering motion, reference frames, and the interplay between fields in modern electrodynamics. While the paradox might seem perplexing at first glance, it underscores the elegance of the laws of electromagnetism and the need to adapt our thinking to new and more comprehensive frameworks as we delve deeper into the mysteries of the universe. Faraday's law, when considered in the context of these more advanced frameworks, remains a powerful and essential principle that continues to shape our understanding of the electromagnetic world. The two-capacitor paradox is a thought experiment within the realm of electromagnetism that presents an apparent violation of the conservation of energy in an electric circuit composed of two ideal capacitors. While this paradox can initially seem to defy fundamental laws, it actually provides a fascinating lens through which we can explore the deeper principles of energy conservation, the nature of idealized components in circuit theory, and the complex interactions that arise in electrostatic systems. In this discussion, we'll break down the paradox in detail, starting with a basic understanding of capacitors, how they store and release energy, and how the system behaves under certain conditions. We will then walk through the details of the paradox itself, examine the underlying assumptions, and ultimately reveal why it is not truly a violation of energy conservation, but rather a consequence of idealized assumptions in the classical treatment of such circuits. Before diving into the paradox, it's crucial to establish a basic understanding of what a capacitor is and how it operates. A capacitor is an electrical component used to store electrical energy in an electric field It consists of two conductive plates separated by an insulating material known as a dielectric. When a potential difference voltage is applied across the plates, positive and negative charges accumulate on the plates, creating an electric field between them. The amount of charge stored on the plates is proportional to the applied voltage. The energy E stored in a capacitor is given by the equation E equals 1 over 2 CV square, where E is the energy stored in the capacitor, C is the capacitance, a measure of the capacitor's ability to store charge. V is the potential difference across the capacitor. This equation is a fundamental principle of energy storage in capacitors, indicating that the energy stored in a capacitor is proportional to the square of the voltage applied across it and the capacitance. Now, let's set up the system that gives rise to the two capacitor paradox. The typical scenario involves two capacitors, initially charged, and a switch that is thrown to connect them together. Here's a step-by-step breakdown of the thought experiment. Consider two capacitors, C1 and C2, with capacitances C1 and C2, initially charged to voltages V1 and V2. Respectively, after charging, the capacitors are connected together in a way that allows charge to redistribute between them. A common configuration is to connect the capacitors in parallel, both positive plates connected together and both negative plates connected together, or in series, positive plate of one connected to the negative plate of the other. After the connection, the total charge in the system remains conserved, but the voltage across the two capacitors may change. The key point is that, upon connection, the charges redistribute between the capacitors, and this process appears to result in a situation where energy seems to be lost or created, depending on how you analyze the system. In the most basic case of ideal capacitors, there's an expectation that the total energy in the system should remain constant. However, the redistribution of energy between the two capacitors raises questions about whether this is actually the case. The crux of the two capacitor paradox lies in the apparent violation of the principle of energy conservation. Let's analyze what happens during the redistribution of energy when the capacitors are connected. Before the capacitors are connected, the total energy stored in the system is simply the sum of the energies stored in each capacitor. After the connection, charge redistributes between the capacitors and the voltages across them change. If the final energy is less than the initial energy, it seems like energy has been lost in the system. But where has the energy gone? In a physical sense, we would expect that no energy is lost unless it is dissipated as heat or electromagnetic radiation, neither of which is expected in an idealized capacitor circuit. In some scenarios, it can appear as though the final energy is greater than the initial energy. This can occur if the redistribution of charge leads to a more favorable configuration in terms of energy storage, which again raises the question of how energy could have been created. The resolution of the two capacitor paradox lies in the fact that ideal capacitors are being considered in the analysis. Ideal capacitors are theoretical components that don't suffer from real-world inefficiencies such as resistance or leakage. In an idealized scenario, no energy is lost to heat and charge is assumed to redistribute perfectly between the two capacitors. However, this idealization leads to some counterintuitive results when the capacitors are connected. The most important of these is the fact that, in an idealized circuit, no external work is done to redistribute the charge between the two capacitors, and yet the energy of the system seems to change. This paradox arises because the redistribution of charge does not necessarily follow the classical expectation of energy conservation in the same way that more complex real-world systems would behave. To resolve the paradox, it's important to consider the behavior of energy in a more nuanced way. The total energy of the system might appear to change due to the way energy is distributed across the capacitors and due to the assumptions about idealized components. Specifically, the distribution of charge and the voltage changes in the system should be carefully analyzed in terms of potential and electric fields, not just the raw energy stored in each capacitor. When the two capacitors are connected, charge redistributes between them. The total charge remains conserved, but because the voltage across the capacitors changes, the energy stored in each capacitor may change as well. The apparent loss of energy is due to the way energy is transferred between the two capacitors. Since energy in a capacitor depends on the square of the voltage, even a small change in voltage can lead to a significant change in the total energy stored in the system. The key to understanding the paradox lies in the relationship between capacitance and voltage. Since the capacitors are connected in a way that allows charge to move between them, their voltages will adjust in response to the redistribution of charge. The final voltage across the two capacitors depends on both their initial charges and capacitances. The total energy in the system is still conserved, but the way it is distributed between the two capacitors and the form in which it is stored may change. The energy loss that seems to occur in the system is not a true violation of energy conservation. It simply reflects the complexity of energy transfer in a system of idealized capacitors. The paradox is rooted in the fact that the components are idealized. In real-world circuits, there are always some inefficiencies, such as resistance and dielectric losses, that would prevent the apparent energy loss or gain seen in the idealized case. When these factors are taken into account, the behavior of the circuit becomes much more intuitive and the paradox is resolved. The two-capacitor paradox does not represent a true violation of the conservation of energy, but rather highlights the limitations and complexities that arise when dealing with idealized components in classical electromagnetism. While the redistribution of charge between two ideal capacitors may lead to an apparent loss or gain of energy, a closer analysis reveals that the energy is simply redistributed in a way that doesn't align with traditional expectations. By considering the ideal nature of the components and the specific dynamics of charge and voltage redistribution, we can reconcile the apparent paradox and gain deeper insights into the nature of energy storage and transfer in electrostatic systems. This thought experiment serves as a reminder of the need to carefully consider the assumptions underlying our models and to recognize that idealized components often behave in counterintuitive ways. In real-world systems, factors such as resistance, leakage, and dissipation of energy would prevent such paradoxes from arising, but in the realm of theoretical physics, they provide an intriguing challenge for our understanding of energy conservation and the behavior of electric circuits.